So this is our fifth topic in our topic, matrices and transformation, which is the first from 4 topic. In our today's lesson, we are going to look at inverse of transformation. Okay, let's first of all read this statement. We use a matrix K to transform an object M to M prime. The transformation which maps M prime back to the original object is called inverse transformation, written as K to power minus 1, which is the inverse of K. The product of the two matrices gives you an identity matrix. So let's take an example. Let A represent a positive quarter turn. Then A inverse, which is A to minus 1, represent a negative quarter turn. So this is a positive quarter turn, so the inverse is a negative quarter turn. A, which is a matrix representing positive quarter turn, the matrix is 0, minus 1, 1, and 0. The inverse matrix, that is a negative quarter turn, is represented by 0, 1, negative 1, 0. So what we are saying, if you multiply the two matrices, that is, you multiply the inverse of A, you multiply by A, then this will give you, we start with 0, 1, minus 1, 0. That is A inverse. You multiply by A, which is 0, minus 1, 1, 0. Giving you 0 times 0 is 0, 1 times 1 is 1. So we add 0 plus 1, you get 1. Then we have 0 times minus 1, that is 0. And we have 1 times 0, that will give you 0. So 0 plus 0 is 0. Minus 1 times 0 is 0. 0 times 1 is 0. So here 0 plus 0 is 0. Minus 1 times minus 1 will give you positive 1. So you note that this is an identity matrix. So when you multiply a matrix by its inverse, it gives you an identity matrix. We can also start with A and we multiply by inverse of A. So this is going to give you, we start with A, which is 0, minus 1, 1, 0. You multiply by A inverse is 1, minus 1, 0. When you multiply, 0 times 0 is 0, minus 1 times minus 1 will give you positive 1. Then this is 1. Then 0 times 1 is 0. Negative 1 times 0 will give you 0. Then we have 1 times 0 is 0. 0 times minus 1 is 0. Then we have 1 times 1 is 1. 0 times 0 is 0. 1 plus 1, 0 is 1. So this is also an identity matrix. So it doesn't matter which one you start with. What we are saying here, that when you multiply a matrix, that is the inverse of A, you multiply by A, it is equals to A multiplied by inverse of A, which is minus 1, and this to give you an identity matrix. So that is very important, and we are going to do an example to demonstrate this. So this is our example 2. And we are told that triangle PQR has vertices P minus 4 minus 1, Q minus 5 minus 3, and R minus 2 minus 3, and our transformation. The triangle is mapped onto another with the vertices P minus 4 minus 1, Q 5 minus 2, R 2 minus 6. Find the inverse matrix of the transformation. Now, here we need to find the matrix. So first we need to find the matrix of transformation. So let's call our matrix of transformation A, B, C, D. And when you multiply this transformation matrix, we have covered this in our earlier lesson. You multiply by the vertices of matrix formed by the vertices of our object. This is minus 4, minus 1. This is minus 5. This is minus 3. This is minus 2, minus 3. When you multiply, it should give you the matrix formed by our image, vertices of the image. So this should give you 4 minus 2. Then we have 5 minus 6, and we have 2 minus 6. So when you multiply this, you'll be able to get minus 4 minus 4a minus b. Then we have minus 5a minus 5a minus 3b. Then we have minus 2a minus 3b. We come to the second row. This will give you minus 4c minus d. Then this is minus 5c minus 3d. And finally we have minus 2c minus 3d. So this matrix is equals to our matrix here, which is 4 minus 2, 5 minus 6, and 2 minus 6. Now, here we are going to solve this. We normally say that corresponding elements of the matrix are the same. So we can see here that if we take minus 4a minus b, it should be equals to 4. So, and then we also minus 5a, this is 4a, minus 3b should be equals to our element here, which is 5. These are simultaneous equation, or two linear equation, which we can solve simultaneously. For us to be able to solve this, we need to eliminate 1. So we are going to multiply our equation by, we multiply this by 3 and this by 1. So we end up with minus 12a minus 3b. Then we have, it is equals to 4 times 3 is 12. Then the other one will remain the same. 5a minus 3b is equals to 5. Now we should be able to eliminate b by subtraction, so that we have minus 3b minus minus 3b, that will be 0. So minus 12 minus minus 5, that should be minus 12a plus 5, and that should give us minus 7. Minus 7a minus 3b minus minus 3b is 0, and 12 minus 5, that should give us 7. Divide both sides by minus 7, divide by minus 7, and therefore we will have our a. So when you divide through by 7, our a is 1. So we substitute our a in one of this equation here. So we have minus 4 times minus 1, which is the value of a, minus b, it is equals to 4. So this is 4. We take minus b, we take 4, minus 4 times 4 is 4. We take it to the other side, this will be 0. Divide by minus 1, divide by minus 1, then you find it implies that b is equals to actually 0. So once we get b, we can now go ahead and solve the other equation. We use the other, that is, we use 4c minus 4c minus d is equals to minus 2, and minus 5c minus 3d is equals to this is minus 6. We multiply the equation by 3 so that, and 1, so that we are able to eliminate our d, and then we have minus 12c. Then we have minus 3d is equals to minus 6, and then we have minus 5c. Then we have minus 5c, minus 3d is equals to minus 6. So we subtract the second equation from the first equation so that we'll be able to eliminate d and be able to get our c. So we can subtract here and we will be able to get, we subtract. Now minus 12 minus 5, this will give you minus 12 plus 5, which is minus 7c. Minus 3 minus 3d will be 0 because it is minus 3 plus 3d, that will give you 0. So this is equals to minus 6 minus 6, that will be minus 6 plus 6, that is 0. So it means 7c minus 7c is equals to 0. Divide both sides by minus 7, you find our c is equals to 0. Now once we find c is 0, we substitute in one of the equation, so we can use minus 4 times 0 minus d is equals to minus 2. Now this will be 0 minus d is equals to minus 2. Divide both sides by minus 1, and then we have our d is equals to, this is minus 1, is equals to actually 2. So we now have found the transformation matrix which we had defined, that A, B, C and D, it is equals to, we have found our A minus 1, our B is 0, our C is 0, and our D is 2. So that is our transformation matrix. Now once you get the transformation matrix, we said that when you multiply the transformation matrix by its inverse, then you should get the identity matrix. So if we write our inverse matrix to be M and WX as our inverse matrix, we multiply by our transformation matrix 0, 2, the product should give us the inverse, the identity matrix, which is 0, 0, 1. So we multiply here, this will be n times minus 1 is minus n, because m times 0 is 0, so here we have minus m. Here we have n times 0 is 0, m times 2 is 2m, so you get 2m. And then we have w times minus 1 is minus w. X is 0, so there we end up with minus w. And here we have w times 0 is 0, x times 2, that will give us 2x. And close the bracket, it should give us 1, 0, 0, 1. So that is our identity matrix. From there, you say we equate the corresponding elements. So minus n is equals to 1, so n is equals to minus 1. And then we have m is equals to 0, because 2m is equals to 0. Divide both sides by m. Then our w is equals to 0, and our x is equals to a half. This implies that our transformation matrix is, because we had defined our inverse matrix as n, we have m, we have w, and we have x, and we have found the values of m, n, w, x. So n is equals to minus 1, m is 0, w is 0, and x is a half. So that is the inverse matrix. And since we had said at the beginning that when you multiply the inverse matrix by the transformation matrix, you should get the identity matrix. Then we can go ahead. So that's the end. But we can go ahead and show that actually this is inverse matrix by multiplying the two matrices, that is our transformation matrix and our inverse matrix, and see whether we'll be able to get the identity matrix. So let's see whether we are correct. So we say it is minus 1 0 0 2, that is the transformation matrix. You multiply by minus 1 0 0 and a half, that should give you minus 1 times minus 1, that is 1. 0 times 0 is 0, so 1 plus 0 is 1. Then we have 1 minus 1 times 0 is 0. 0 times a half is 0, so there we have 0. 0 times minus 1 is 0. 0 times 2 times 0 is 0, so we have 0. Then 0 times 0 is 0. 2 times a half is 1. So that is our transformation, that is our identity matrix. This is the matrix that we got, 0 0 1, which is the identity matrix, which proves that this matrix that obtained here is the inverse of this. So it was a bit lengthy, but I hope you have followed the process, and that is, you can always watch it again, see whether you will be able to follow. From there, we are going to look at the relationship between the area scale factor and the determinant of the transformation matrix. So, in this section, we are going to deal with the relationship between area scale factor and the determinant. In any transformation, the ratio of area of image to area of the object is known as area scale factor. In short, written as ASF, area scale factor. And that is, area scale factor is equals to area of the image divided by the area of the object. The determinant of a matrix is the difference of the product of the elements of main diagonal and the other diagonal. That is, if we are given the matrix A, B, C, and D, determinant product of AD, that is the main diagonal, and minus the product of the elements of the other diagonal. So that is the other diagonal. So that is how we calculate the determinant. Now, from the determinant, so the relationship between the determinant and the area scale factor is that they are numerically equal. The area scale factor is numerically equal to the determinant. Where the determinant is negative, ignore the negative side and take the value to be the determinant, which we are saying that it is equals to the area scale factor. So we are going to do an example and demonstrate that and see whether we will be able to get it clearly. So we have an example here whereby we are told that triangle OAB, whose vertices are 0 0, and we have A 3 0, we have B 3 2, was transformed through the matrix minus 3 0 0 minus 3. Find the image area of the area scale factor and show that the determinant is equals to the area scale factor. So this is our transformation matrix, and we pre-multiply with the matrix that is formed from the vertices of our object, and that is 0 0. We have 3 0, and we have 3 2. Close the bracket. It is equals to the matrix that is to be formed using the image vertices. So we have our OAB. Our other matrix, we have 0 0, the matrix formed from the image 0 0. We have minus 9. We have minus again when you multiply minus 0 times 3 and minus 3 times 3, we also have minus 9. Then we come to the second row. You have 0 times 0 and minus 3 times 0, we get 0. So the other row we start with 0. Then the other will be 0 times 3 is 0, and minus 3 times 0 is 0, we get 0. And the other one will give us minus 6, that is 0 times 9, 0 minus 3 times 2, you get minus 6. So these are the vertices of our image O prime, A prime, and B prime. So we go ahead and we plot our figures on a Cartesian plane. So here we have the Cartesian, our graph, our grid we are going to plot. So we start by preparing our Cartesian plane. So we have the x-axis up to number 6, followed by y-axis, and then up to 4. Then we fill the negative side where we have minus 2, minus 4, minus 6, and we have the negative side of x up to minus 9, because the lowest value of x is minus 9. We then identify, we start by our object. So O is at 0, 0. Our A is at 3, 1. So that's where we have our O. Then we go to 3, 1. And our B is at 3, 2. So we join the 3 points to come up with our object. So from there now we plot our image. We have O is at 0, 0. So it lies the same place as the other O, the origin. Our A prime is at minus 9, 0. That's where we have our A prime. And our B prime is at minus 9, minus 6. So that is where we have our B prime. Then once we identify that, we join the 3 points to come up with our image. So we now have our image OAB double prime, and then from there we are required to find the area image, which we have done. We need to find the area scale factor. The area of the image is a half base times height. So that is will give us 2 divided by 2 is 1. So there we have 3. We then get the area of the image, which is a half base times height. That is, we will be able to get a half multiplied by 9 multiplied by 6, and that should give us 9 times 6 would give us 27. 6 divided by 2 is 3, 27. Now from there, area scale factor, we have said it is equals to area of the image divided by area of the object. So it is 27 over 3, and that should give us 9. Then from there we get the determinant of our transformation matrix. Since our transformation matrix is minus 3 times 0, 0 minus 3, it will be minus 3 times minus 3 minus 0 times 0, which should give us 9. So we can clearly see, as we are told, that the determinant of the matrix is equals to the area scale factor, and that is what we wanted to achieve. So that brings us to the end of that lesson. So after this, we are going to look at another new transformation known as shear, and also another one known as stretch. So you are welcome to our next lesson, which will be finalizing this topic. So thank you for watching.